Welcome to today's deep dive. Today, we have a really interesting stack of source material, specifically an instructor's manual on pressure transmitters from a skilled trades learning resource.
Yeah, it's a pretty comprehensive guide.
It really is. And our mission today is to kind of demystify how modern industry measures these, invisible forces that keep our world running safely. We're talking about the pressure, the flow, and, well, the level of fluids.
Right. And our goal is to extract the absolute best insights from this manual so you, the listener, can understand this completely hidden world.
Exactly. Because to understand why this matters, I want you to imagine that you're sitting like maybe a few miles away from a massive industrial plant right now.
Hmm.
Maybe it's an oil refinery or a chemical processing facility or even a power station.
Just a completely normal part of the landscape.
Right. But inside that plant, there are miles of pipes carrying highly explosive gases, incredibly toxic fluids, and steam that's so hot it could just easily melt standard metals.
Yeah, it is just a staggering amount of volatile energy. And it's all contained and moving at incredibly high speeds under extreme pressures.
And the people running that plant, they're sitting in this secure air-conditioned control room, but they need to know exactly what the pressure of that explosive gas is at any given fraction of a second.
Which brings up a rather terrifying mechanical problem, honestly.
Oh, for sure. Like, how do you safely measure something that inherently wants to blow up
Hmm.
without actually blowing up the control room?
Right. And the answer lies in this piece of unsung, absolutely brilliant engineering that we're unpacking today.
The pressure transmitter.
Exactly. These instruments are literally everywhere in the infrastructure around you, but they're completely invisible to the average person.
So let's kind of frame this with a metaphor. Think of an industrial plant as a giant human body.
Okay, I like that.
So the control room, where the operators monitor all their screens, that's the brain,
Hmm.
and the thousands of miles of pipes, those are the veins and arteries. But the plant can't actually feel anything without a nervous system. Like the brain needs to know if the blood pressure is too high, right? So pressure transmitters serve as the nerve endings of this giant body.
Yeah, they physically interact with those sensations, like a crushing pressure or a flowing liquid, and they translate them into signals that the brain can actually read and react to.
Right, just like your biological nerve endings keep your hand from, burning on a hot stove by sending a really rapid signal to your brain.
Exactly. These transmitters keep the plant from experiencing a catastrophic failure.
So to understand how these modern nerve endings work, with all their high-tech electronics and stuff, we actually need to look backwards first.
Yeah, we have to look at the purely mechanical way early engineers solved this problem. Because before transmitters were invented, the solution was, well, it was less than ideal.
That's putting it mildly.
Yeah.
According to the sources, in the early days of industrial processing, if an operator wanted to know the pressure of a toxic, highly pressurized fluid, they literally piped that fluid directly into the control room.
Yeah, they just hooked it up to a physical pressure gauge right there on the desk.
Wait, really? They just brought the hazard right into the room with them.
I mean, yes, you are bringing the primary hazard directly to the human operators.
That is insane.
It was, because if that glass gauge shatters or the little copper line feeding it develops a leak, your control room is instantly filled with flammable or lethal material.
So they obviously had to invent a way to keep that hazard out in the field.
Right. And their solution was the pneumatic pressure transmitter. The manual we're looking at highlights some classic models like the Foxborough 13A and the 45P.
Okay, so how did those work?
Well, the overarching idea was to use standard clean air pressure to send the signals instead of the actual hazardous fluid.
Oh, okay, so that was a massive leap forward in safety then.
Absolutely massive. Instead of piping explosive gas to the control room, you pipe the explosive gas into a heavy-duty isolated steel box out in the field.
And that box is the transmitter.
Exactly. Inside that box, the dangerous process pressure pushes against this flexible metallic diaphragm. And that physical push is then mechanically converted into a safe proportional air pressure signal.
Which then travels through a tube back to the operators.
Yeah, got it.
But the way it converts that physical push into an air signal is, honestly, it's fascinating. The sources describe this whole maze of internal components like force bars, flexures, baffles, and nozzles.
Yeah, it sounds complicated, but the core principle it relies on is something called moment balance negative feedback.
Moment balance, negative feedback. Okay, break that down for us.
So moment balance essentially means that the internal mechanical system is constantly working to reach a perfect equilibrium.
Like it's trying to balance itself out.
Right. So in a device like that Foxborough 13A, when the dangerous process pressure pushes the diaphragm moves a rigid metal rod, which is called a force bar.
Okay.
And that force bar acts like a lever. It moves a tiny flat plate, that's the baffle, closer to an air nozzle that is continuously blowing a small amount of clean air.
Oh, I see. It's kind of like putting your thumb over the end of a running garden hose. As your thumb gets closer to the opening, it, restricts the flow, and the water pressure builds up inside the hose behind your thumb.
That is a perfect analogy because in the transmitter, that buildup of back pressure is deliberately captured. It's actually routed into a little metal sort of accordion-like component called a feedback bellows.
Okay, accordion.
Yeah, and as the back pressure builds, that bellows inflates. And as it inflates, it physically pushes back against the linkage, moving the baffle slightly away from the nozzle again.
So it's fighting back against the initial push.
Exactly. The system keeps moving until the forces perfectly balance out. So the physical push from the dangerous process fluid equals the physical push from the inflated bellows.
Wow. So the system literally finds its own balancing point. And that resulting back pressure, the air that's currently sitting in the tube, that becomes the actual output signal going back to the control room.
Right. That balancing act is the moment balance. And it's incredibly reliable because it's entirely self-correcting.
Because if the process pressure drops, the baffle moves away, the back pressure drops, the bellows deflate slightly, and boom, a new balance is found.
Exactly. But these mechanical devices still need to be calibrated for different tasks.
Right, the manual talks a lot about adjusting the zero and the span on this internal linkage called a range bar. Let me try another analogy here to visualize this because it's kind of tricky.
Go for it.
I picture this moment balance system like a playground seesaw. So you have a kid on one side, and they represent the input pressure, and you have a kid on the other side representing the output signal.
Okay, I can see that. Building on that, adjusting the zero is essentially adding a permanent bias force to the system.
Like hanging a heavy backpack on one of the kids.
Yes. It's exactly like giving one kid a backpack so the seesaw starts at a completely different baseline angle.
Yeah.
In the actual transmitter, technicians literally tighten or loosen a tension spring, the zero spring, to pull on the range bar and shift that entire range of measurement up or down by a set amount.
Okay, that makes sense. And then we have the span. So changing the span is like physically sliding the center pivot point, the fulcrum of that seesaw, to the left or right.
Right.
Because if you move the fulcrum much closer to one kid, they suddenly have a lot more mechanical leverage.
Right.
A tiny push from them creates this massive movement on the other side.
Exactly. In the actual transmitter, you are turning a piece called the range wheel, and you're moving it up and down a threaded rod to change the length of that pivot. By changing that pivot point, you change the gain of the instrument.
So you're dictating exactly how much of an input pressure change is required to create a full output signal change.
Right. It is pure tactile mechanics, just relying on physical leverage and air.
Which is brilliant. But that brings up a pretty logical question. If this pneumatic air pressure system is so safe and reliable and, elegantly balanced, why did the industry ever abandon it for electronic transmitters?
Well, it really comes down to two absolute limits of physics as industrial plants grew larger: speed and distance. An air pressure signal travels through a tiny copper tube at, well, roughly the speed of sound. Now, if your control room is 50 feet away from the sensor, that delay is negligible.
Right, you wouldn't even notice.
But if you are building a sprawling, modern oil refinery, and the control room is a full mile away, that pneumatic signal takes several crucial seconds to arrive.
And if you have a sudden catastrophic pressure spike in a boiler, those seconds are literally the difference between an automated safety shutdown and a total disaster.
Exactly. Electronic signals, on the other hand, travel virtually instantaneously over copper wire. They allow for massive facilities and split-second control loops. So the industry was basically forced to move from air to electrons simply to keep up with the scale of the plants.
But, we've solved the distance problem, but didn't we just create a new physics problem?
Oh, yeah.
Because air has physical mass, right? It can push a lever or inflate a bellows.
Yeah.
Electrons don't really work that way.
No, they don't.
So the transmitter needs a completely different way to physically feel that pressure.
Right. It has to rely on materials that fundamentally change their electrical properties when they are physically deformed.
Okay, like what?
Well, the manual highlights a few methods, starting with capacitance elements. So a basic capacitor consists of two metal plates separated by an insulator.
Got it.
In a pressure transmitter, one plate is fixed, and the other is a flexible measuring diaphragm. And the space between them is filled with a dielectric fluid, like silicone oil.
Oh, I see. So when the process pressure pushes on the sexible plate, it squeezes closer to the fixed plate. And moving those plates closer together actually changes their capacity to store an electrical charge.
Exactly. And then the internal circuitry measures that change in capacitance and translates it into a pressure reading.
That's super clever.
It is. But another primary method, which is incredibly common, is the use of strain gauge elements.
Strain gauges. Okay.
Yeah, these operate by deliberately stretching metal or silicon. The fundamental principle is that if you take an electrical conductor, like a wire, and you change its physical dimensions, so its length and its cross-sectional area, its electrical resistance changes.
Okay, let me try another analogy. Imagine a piece of silly putty.
Okay.
If you pull the silly putty apart,
Yeah.
it gets longer,
Right.
but it also gets thinner in the middle. The cross-section shrinks.
Exactly.
So that same physical deformation happens to the wire filament in a metallic foil strain gauge. Like when pressure pushes on the diaphragm it's glued to, the metal stretches, gets thinner, and suddenly it is much harder for the electricity to push through.
You nailed it. The system measures that drop in current and registers an increase in pressure. And we are talking about microscopic deformation here.
How small are we talking?
Well, the manual describes metallic foil strain gauges with a wire filament grid that is just 0.025 millimeters thick. Yeah, that's a fraction of a human hair. And beyond metal, modern transmitters frequently use semiconductor gauges made of silicon. The source notes that these silicon gauges are actually 25 to 100 times more sensitive than metallic foil.
Oh, wow. So they can detect just microscopic fluctuations in pressure.
Exactly, but they are highly nonlinear, which is a challenge.
Okay, but wait. There is a massive inherent physical flaw in this design. If we just stick a single wire out in the real world,
Oh, what's that?
metal expands when it gets hot, right?
Right.
So if this strain gauge is sitting outside on a piping hot summer day at a refinery in Texas, the ambient heat alone is going to stretch that wire. Wouldn't the transmitter's computer look at that stretched, highly resistant wire and be tricked into thinking a huge pressure spike just happened, like triggering a false alarm?
That is a brilliant observation. That phenomenon is called temperature drift. And without a solution, it would render the sensor completely useless in an outdoor industrial setting.
So how did they fix it?
Engineers solved this using a brilliant workaround called temperature compensation. They utilize a circuit known as a Wheatstone bridge, and they introduce something called a dummy gauge.
A dummy gauge. Okay, what is a Wheatstone bridge first?
A Wheatstone bridge is essentially a diamond-shaped electrical circuit that's designed specifically to measure comparative resistance. It splits an electrical current down two separate paths and compares them.
Oh, I see where this is going.
Yeah.
So inside the sensor, they don't just install one strain gauge on one path of that bridge. They include a second duplicate strain gauge on the other path. And that's the dummy.
Exactly. It is mounted right next to the active gauge, meaning it is exposed to the exact same ambient temperature of that hot summer day.
Yeah.
But, and this is the key, it is physically shielded from the actual pressure strain of the process fluid.
Oh, that is so smart. So when the ambient temperature spikes, both the active gauge and the dummy gauge stretch from the heat. The electrical resistance goes up equally in both paths of the circuit. And because the Wheatstone bridge measures the difference between the two paths, the temperature errors perfectly cancel each other out.
You got it. The only difference the circuit ends up measuring is the physical strain caused by the actual pressure pushing on the active gauge.
So it literally uses the environmental problem to solve the environmental problem.
It's elegant, right? But surviving the ambient temperature is really only half the battle. Because the transition from a perfectly compensated sensor in a clean laboratory to a device bolted onto a pipe in the brutal real world, that's where many instruments fail.
Yeah, the physical reality of the plant dictates everything, which I guess is why the source manual heavily focuses on, like, functional specifications and impulse lines.
Exactly. The manual breaks down transmitter specifications into two distinct buckets, performance specs and functional specs.
Okay, performance is like the accuracy and stability, right? Like how well the instrument does the math.
Right. And functional specs are pure survival parameters. What are the absolute temperature limits? What is the overpressure protection? Are the materials NS certified?
NES certified. What does NES stand for?
NES stands for the National Association of Corrosion Engineers, and this certification is critical because if you are working in environments extracting ferrogas, you are dealing with high concentrations of hydrogen sulfide.
Which is bad news.
Very bad news. Hydrogen sulfide doesn't just corrode standard steel, it causes something called hydrogen embrittlement. The atomic hydrogen actually permeates the crystal lattice of the steel.
Whoa.
Yeah, making it incredibly brittle until it literally shatters under pressure.
So to survive that, the parts of the transmitter that actually touch the fluid, the wetted parts, the O-rings, the isolating diaphragms, they have to be forged from specialized, highly resilient alloys, right? Like Hestaloy or Monel.
Absolutely. And attaching these high-tech sensors to the main pipes relies on surprisingly old-school plumbing geometry. They use tubing called impulse lines to connect the main process pipe to the remote transmitter.
And standard practice dictates those impulse lines must be at least a half-inch in diameter,
Hmm.
because any smaller and the particulate matter from the process will just quickly block the tube entirely.
Exactly. And they seal the threaded connections with exactly 2.5 wraps of Teflon tape and a specialized sealant like a Noan 60 jet lube.
Right. But what I love is that the specific installation hacks they use depend entirely on the substance they are measuring, and they rely heavily on just basic gravity as a natural filter.
Yeah, gravity is a technician's best friend. Take steam, for example. You have steam roaring through a pipe at 1,000 degrees. If that steam touches the silicon sensor, it melts the internal components instantly.
So to protect it, technicians tap into the side of the main pipe, mount the transmitter physically below the tap, and fill the impulse lines with cold water.
Right? Those are called wet legs.
Wet legs. And the high-pressure steam pushes on the column of cold water, and then the cold water pushes on the transmitter's isolating diaphragm. So the steam itself never actually reaches the sensor.
Exactly. And if they are measuring a liquid process, they use a different geometry. They tap the side of the pipe, but they pitch the impulse lines upward.
Upward.
Yeah, the standard is an incline of at least 8 centimeters per meter. This way, if any stray gas bubbles get trapped in the liquid line, gravity and buoyancy cause them to naturally float up and away from the sensor right back into the main pipe.
It's literally just like putting a trap under a bathroom sink to keep the bad stuff out.
It's the exact same principle.
Yeah.
And conversely, if they are measuring a gas, they pitch the lines downward so any liquid condensation continuously drains away from the measuring instrument.
Because $1 million control system is entirely blind. If a $10 piece of stainless steel tubing is installed at the wrong angle and traps a gas bubble.
Completely useless.
But even with NAS-certified metals and clever gravity traps, I mean, the corrosive process fluids and extreme temperatures eventually take a toll, right? These instruments wear out, their calibration drifts, or they simply break.
They do, and that creates a massive logistical nightmare because you can't just unscrew a broken sensor from a live, highly pressurized pipe to replace it.
Yeah, that would cause a catastrophic leak.
Exactly. Which brings us to a crucial piece of maintenance hardware, the manifold. Instead of threading the transmitter directly into the impulse line, they install a manifold block between the process and the sensor. A very common type is the 3-valve manifold.
So it's a solid block of machined steel containing 3 interconnected valves.
Right. And this allows an instrument technician to walk up to the device, turn a few specific handles, and completely isolate the process pressure from the sensor.
Oh, nice. So then they can safely open a bleed valve to vent the tiny amount of trapped fluid, hook up their portable calibration gear, repair the transmitter, and put it right back online.
And all of this happens while the billion-dollar chemical process continues to run uninterrupted right behind those closed block valves.
That is incredible. But once the sensor is repaired and recalibrated, it obviously has to send its data back to the control room. And for that vast network of sensors to function as a cohesive nervous system, they require a common language.
They do. In industrial automation, that language is strictly standardized by the ISA, the International Society of Automation, specifically ISA Standard 5.1.
Right. They dictate the symbols used on the engineering blueprints, which are known as piping and instrumentation diagrams. And they dictate the actual signal standards so that a sensor built by one company can, seamlessly talk to a computer system built by another.
Exactly. So going back to our early pneumatic transmitters, the air pressure devices, their standard vocabulary was 3 to 15 pt pounds per square inch gauge.
Or in metric, that's 20 to 100 kilopascals.
Right. But when the industry transitioned to electronic transmitters, the new universal standard became the 4 to 20 milliamp current loop.
And the manual specifically emphasizes why the industry adopted a current loop measured in milliamps instead of a voltage loop, like, say, 1 to 5 volts.
Yeah, it's a really important distinction, because if you send a voltage signal over a wire that is a mile long, the natural electrical resistance of that long run of copper wire will cause the voltage to drop by the time it reaches the control room.
So a 5-volt signal leaving the transmitter might show up as, like, 4.5 volts at the computer.
Exactly. And the system interprets that voltage drop as a sudden drop in process pressure, which is entirely false.
But a current loop doesn't care about line resistance. If the transmitter regulates exactly 20 milliamps of current into the wire, exactly 20 milliamps will flow through the entire loop and arrive at the other end.
Right. And it is also highly immune to electrical noise from nearby industrial motors or power lines.
Okay, but looking at these standard ranges, 3 to 15 psi or 4 to 20 milliamps, I have a glaring question.
Let's hear it.
If there is zero pressure in the pipe, shouldn't the signal be zero? Why on earth does the measurement start at 3 psi or 4 milliamps?
I love this question. Because that baseline offset introduces one of the smartest safety features in all of engineering. It's known as the live zero, or the lower range value offset.
Okay, live zero.
Let's look at the safety aspect first. Imagine your electronic signal standard with simply 0 to 20 milliamps. Zero pressure equals 0 milliamps.
I mean, that seems logically intuitive to me.
Right. But now imagine a piece of heavy machinery accidentally digs up the trench outside and severs the wire connecting your transmitter to the control room.
Ooh.
The electrical current on a severed wire immediately drops to absolute zero. The control room computer sees 0 milliamps.
And the operators have literally no way of knowing if the process pressure safely dropped to zero or if they have a catastrophic communication failure while the pipe is actually, like, overpressurizing.
Exactly. A zero signal is dangerously ambiguous. So by utilizing a live zero setting the absolute bottom of the measurement scale to 4 milliamps, a true zero pressure reading sends an active 4 milliamp signal to the control room.
Oh, that is so smart. Because if the signal ever drops to absolute 0 milliamps, the computer instantly recognizes that the wire is broken or the power has failed, and it triggers an immediate safety alarm.
Exactly. It is a built-in fail-safe diagnostic.
And then the manual lists two other highly practical reasons for the Live Zero 2. The first relates to mechanical momentum. Any mechanical device like a pneumatic flapper valve or a control relay responds better and faster when it's already slightly energized or moving, rather than trying to overcome the initial dead-stop friction of true zero.
Right, it keeps things primed. And the final reason applies specifically to the electronic 4 to 20 milliamp loop. That constant minimum baseline flow of 4 milliamps provides just enough electrical background juice to physically power the internal microprocessors and the sensor arrays inside the transmitter itself.
So because the loop never drops below 4 milliamps, the engineers don't even need to run a separate, dedicated power cable out to the sensor. The device just powers itself directly off the communication line.
It is incredibly elegant and efficient.
It really is. And for you listening right now, this means that behind the scenes of your daily routine, there's this invisible web of meticulous engineering keeping things running.
Truly everywhere.
Yeah, whether you are pouring a glass of tap water, turning on your gas heater in the dead of winter, or filling your car at the pump, you are relying on these hidden, highly sensitive nerve endings. Because of ingenious hacks like dummy gauges canceling out the summer heat, gravity-pitched impulse lines keeping sensors dry, and the brilliant fail-safes of live zeros. These massive, inherently dangerous automated systems run safely and silently in the background of modern civilization.
It really is a remarkable triumph of practical engineering. And as we look to the future, I want to leave you with a final thought to mull over based on everything we've talked about today.
Oh, let's hear it.
We learned that semiconductor strain gauges are up to 100 times more sensitive than metal ones, but they suffer from being highly nonlinear. Now, currently, these transmitters are rapidly being paired with advanced artificial intelligence and machine learning right at the device level. So imagine a world in the very near future where the transmitter doesn't just send a raw pressure reading to a human operator, but it mathematically corrects its own nonlinearity in real time. And even further, it continuously analyzes the microscopic acoustic vibrations in the pipe's fluid.
Wait, acoustic vibrations?
Yeah. The transmitter itself could mathematically predict a catastrophic structural rupture or a valve failure hours or even days before a human operator even knows there is a problem. We might soon see a world where every single pipe in a factory is a hyper-aware, self-correcting nervous system.
The plant body, evolving to diagnose its own illnesses before the symptoms even show up on a screen. I love that. And on that incredibly futuristic note, we're going to wrap up today's deep dive. We hope you never look at a pipe or a seesaw or a bathroom sink the same way again.